Thank you for attending our webinar today. My name is Ryan McLennan, and I'll be giving the presentation or webinar. I'm a professional engineer with sulfur recovery engineering, more specifically a lead process engineer. We at Sulfur Recovery Engineering help our clients, typically at gas plants and oil refineries worldwide, ensure that the operation of their sulfur recovery units and also their amine and gas treating units are performing well. Today's webinar is the third in a series of webinars provided by Sulfur Recovery Engineering. The first webinar that we presented back in the spring was on the dynamic simulation of SRUs by way of VMG Sim. The second webinar presented in June was on specifically Claus condensers and sulfur fires. If any of those webinars are of interest to you, please don't hesitate to contact us. Our website is www.sulfurrecovery.com, and also by email. My email is ryanm@sulfurrecovery.ca, and I will type that into the questions tab. So if anything does come up, please do not hesitate to send me an email. Today's webinar focuses on Claus Converters, a very important process unit within the sulfur recovery unit. Here is the driving force for overall sulfur recovery, where we react H2S and SO2 to form elemental sulfur in the vapor state. After a converter, we have a condenser where we take the elemental sulfur in the vapor form and produce essentially the final product in the SRU, which is liquid sulfur. To begin, we will discuss the reactions that are taking place within the sulfur recovery unit. Upstream of the Claus converters, we have the reaction furnace. In the reaction furnace, we initially process the sulfur load coming into our SRU, specifically in the form of H2S. In the reaction furnace, we add an appropriate amount of air such that we combust H2S and form SO2, which is denoted in the first reaction on this slide. As soon as we produce SO2 in the reaction furnace, H2S that is remaining, that was not burnt to form SO2, reacts with that SO2 to form sulfur vapor. In terms of conversion, specifically the conversion of H2S to elemental sulfur, in the reaction furnace, we can achieve up to 75% of initial sulfur or H2S conversion. The remainder is taken care of downstream in our Claus converters. Claus converters are packed with catalyst, and the reaction that takes place across a Claus converter is where we react 2 molecules of H2S and 1 molecule of SO2 to produce sulfur vapor. This reaction is formally known as the Claus reaction, where we react 2 molecules of H2S and a molecule of SO2 to produce sulfur vapor and water. This reaction is exothermic, and we will discuss in a later slide what that means in terms of assessing the performance and catalyst activity levels in a Claus converter. Here's a picture of a series of 3 Claus converters present at a large gas processing plant in Alberta, Canada. A series of 3 Claus converters. In the Claus converter, again, we react 2 molecules of H2S and 1 molecule of SO2 to produce sulfur in the vapor form. Downstream of each converter is a condenser, and it's in the condensing unit that we actually take the sulfur vapor that we generated in the Claus converter and we condense it to form essentially the final product from the SRU, which is liquid sulfur. Here we have 3 Claus condensers. Now, in terms of nomenclature, SRUs overall are quite similar. However, there is different ways to set up the various process units within the SRU, and with that there are some differences in terms of nomenclature. A Claus converter is the same as a Claus reactor. The same thing. Sometimes when we visit sites, a Claus converter or a Claus reactor may be termed as the first catalytic stage, which would be the same as the first Claus converter, the first Claus reactor. We could also have the second catalytic stage, which is the same as our second Claus converter and our second Claus reactor. On the previous slide, in terms of the reactions that take place in the SRU, more specifically though in the Claus converters, we have the Claus reaction. The Claus reaction is optimized when we are able to react 2 molecules of H2S and 1 molecule of SO2. In the front end of the process, at the reaction furnace, we add an appropriate amount of air to combust a portion of the total H2S coming into the plant by way of our feed streams. At gas plants, that's primarily a feed stream from our amine unit, and at refineries, we have an additional feed stream known as the sour water stripper. Both contain a large proportion of H2S. In the reaction furnace, we combust a portion of that total H2S to make an appropriate amount of SO2, such that everywhere in our process, we have our optimal ratio of 2 molecules of H2S plus 1 molecule of SO2, which will yield sulfur in the vapor phase. It's important to remember that the Claus reaction occurs in the gas phase. The product from the reaction is sulfur vapor. So sulfur vapor in the gas phase. Also, the Claus reaction is equilibrium limited. That is the reason why downstream of each Claus converter we have a condenser. If we are able to remove our product from the process, we remove sulfur vapor in the form of liquid sulfur in the condenser, the gas then flows to the next Claus converter or catalytic stage where we can reestablish a new or higher level of the extent of the overall Claus reaction in our process. In terms of reaction chemistry, again, a ratio of 2:1 H2S to SO2 optimizes the Claus reaction. We will see in a future slide that the Claus reaction is also impacted by operating temperature. The Claus reaction in general is favored as we reduce operating temperature. However, the reaction itself is gas phase, and in any converter bed, we would not want to form any liquid or solid sulfur. For that reason, the optimal operating temperature in a Claus converter is typically 5 to 10 degrees Celsius or 10 to 20 degrees Fahrenheit above the converter bed specific dew point. So the temperature upon which the sulfur vapor in the overall mixture would condense. We have a picture here of a Claus converter. Gas coming in the top. We have a bed of catalyst of a certain depth supported by grating. The reaction occurs inside or on the internal area of the Claus catalyst, which is extremely porous, a very high internal surface area. So again, the Claus reaction takes place inside the pores of our Claus catalyst. In terms of optimizing the Claus reaction, again, the reaction itself is optimized when we're able to react 2 molecules of H2S and 1 molecule of SO2 to form sulfur. At the same time, we saw that the Claus reaction is also favored as we are able to reduce our operating temperature. On the bottom of this plot, we have the amount of excess air in our process. At the final condenser in our process, we have a tail gas analyzer which measures the concentration of both H2S and SO2 in our system. We know that the Claus reaction itself is optimized when we have a ratio of 2 to 1 in our process. An excess air signal or value of 0 corresponds to an H2S to SO2 ratio of 2. Thus, we see for an excess air value of 0, we have optimal recovery or percentage in our process. Now, this signal is sent back to the front end of our process where we are adding air, and it serves as fine-tuning of that air addition or introduction. We see that for an excess air signal of approximately minus 0.5 to 0.5, we don't have much of a drop off in terms of our overall recovery level. Thus, proper steady operations, we strive for a signal from our tail gas analyzer between minus 0.5 and 0.5 in order to ensure that our Claus reaction is optimized from a stoichiometry perspective. Some design principles for our converters. In general, we have process gas coming from an upstream condenser coming in the top. One of the most important takeaways from this diagram is proper inlet gas distribution. The Claus reaction itself, as I discussed, takes place internally, so inside the pores of our Claus catalyst. It makes sense that in order to maximize the extent of reaction possible, we would want to have good distribution of our process gas such that it covers the entire bed of our catalyst. From field experience, especially in Alberta, where the overall sulfur loading or sulfur levels or load to the SRU is declining due to wells that are becoming less sour, so less H2S overall. Struggle with oversized converters and achieving desired conversion or recovery levels. Inlet distribution is very important such that we maximize the available amount of surface area for the reaction to take place. We see that we have a bed of catalyst supported by grating. Sometimes above the grating, we will have inert substances to also, or balls, to help associate with the distribution of gas outside and exiting the Claus converter. One other feature is that the inside of a converter is always lined with fire brick or castable refractory. These vessels are typically made out of carbon steel. Thus, since the reaction occurring in the bed is exothermic, thus with reaction we have an increase in temperature in our bed, we want to ensure that the integrity of the carbon steel is not jeopardized by any temperature excursions or runaways that do happen in the converters from time to time, especially during SRU shutdown and startup procedures. To summarize, we talked about refractory lined converters in order to protect the carbon steel vessel shell from temperature excursions. It's important to have quality process gas distribution across our bed of catalyst. We want to minimize any channeling that could occur. Again, we are able to better promote the Claus reaction if we are able to maximize the available amount of surface area for the reaction to occur. Gas will travel or go through the bed in a path of least resistance. So we want to make sure that we don't have any channeling occurring, and that could be helped by proper inlet distribution. Typically in most converters, again, depending on the total amount of sulfur coming into the SRU, so the total amount of H2S that needs to be processed, typically we have 2 to 5 feet of depth in terms of catalyst in our converters. Design or bed depth is determined by maintaining an appropriate gross hourly space velocity, essentially residence time for the reaction to achieve equilibrium. In each converter bed, the Claus reaction must achieve equilibrium to ensure that we are able to achieve quality and acceptable overall sulfur recovery levels in our process. Also, temperature indication in our converters is extremely paramount. We recommend at least 3 levels of temperature indication. So top, middle, and bottom in our beds, for example, and also temperature indication across each section. Temperature indication is extremely important to be able to assess from the DCS the extent of the Claus reaction that is occurring. We will be able to assess this by way of temperature profiling. And also temperature indication across a bed will give us a good indication in terms of catalyst activity, or, the most popular question that we receive from our clients is, we have a turnaround coming up. Do we need to replace our catalyst? As we'll see in a future slide, temperature profiling of our converter beds can provide some pretty good information in terms of where we stand going into a turnaround, and if there's a question in terms of, does my catalyst need to be replaced, or will it last another, say, 4 years? Claus converter performance. We talked about optimizing reaction stoichiometry, that 2-to-1 ratio. We also talked about how if we can achieve specified operating temperatures, we can also improve the conversion level across a Claus converter. If we look at the plot below, we have temperature on the x-axis and we have percent conversion. So percent conversion, let's think of H2S that will be converted to sulfur. At the thermal section, which is our reaction furnace, we burn a portion of our total H2S and form SO2. Again, as soon as we form SO2, it can react and will react with the H2S that we have remaining, and we will form sulfur vapor. We see that for typical reaction furnace temperatures, typically north of 1800 degrees Fahrenheit, we can achieve upwards of 75% of initial sulfur conversion in our thermal stage. Whatever H2S and SO2 is remaining, that's what we take care of in our catalytic sections. As we move to the left, as we reduce temperature, because we know that the Claus reaction is favored as we are able to reduce temperature, we see that our overall conversion approaches that of 100%. Unfortunately, the Claus reaction is equilibrium limited. Thus, no matter what we do or what processes we employ downstream, we will never actually achieve 100% conversion. For this reason, and because converter operations are further optimized as we reduce converter operating temperature, we recommend a operating temperature that is 5 to 10 degrees centigrade or 10 to 20 degrees Fahrenheit above the bed-specific dew point temperature. Again, that temperature is a temperature upon which the process gas stream in our converter, including our product, sulfur vapor, would condense. The reaction itself is gas phase. We do not want to be forming liquid sulfur or solid sulfur in our reactors. Liquid sulfur and solid sulfur would impact the available area, the available surface area for our reaction to take place, essentially plugging off our catalyst pores. Here we have a picture of alumina catalyst, and to the right we have a depiction of what it might look like inside the internal structure of our catalyst. We see the pores. We see that since the reaction takes place inside of our catalyst beads, that there is a lot of available surface area for the reaction to take place. There are typically two catalyst types that are employed in our SRU. One is alumina catalyst, and the second is a special Titania catalyst. The alumina catalyst is excellent. It is cheaper than our specialized Titania catalyst. However, there is one drawback. In the reaction furnace, as you can probably imagine, there are so many different reactions taking place. Specifically, side reactions where sulfur is trapped in species that do not participate in the Claus reaction. We want to react 2 molecules of H2S with 1 molecule of SO2. In the reaction furnace, our feed streams contain hydrocarbons. They also contain CO2. Thus, in the reaction furnace, we do have some undesirable side reactions that take place. specifically the formation of COS, or carbonyl sulfide, which is formed by the reaction of CO2 and H2S. Also, hydrocarbon can react with H2S and form what's called carbon disulfide, or CS2. In general, the primary goal or objective of our first catalytic converter is to reconvert COS and CS2 into a form, specifically H2S, which then in the next catalytic converter could react with SO2 to form sulfur vapor. The hydrolysis reactions, so COS and CS2 plus water, yield H2S, and this is the primary focus or reaction that takes place in our first catalytic bed, which brings us back to the differences between alumina catalyst and Titania catalyst. Titania catalyst is much more effective in terms of carrying out these hydrolysis reactions. For fully active, full Titania catalyst, generally this catalyst contains greater than 85% titania. We will achieve 95+% rehydrolysis of COS and CS2 to form H2S. Another excellent takeaway from Titania catalyst, not only is it more effective at performing these hydrolysis reactions compared to alumina catalyst, typically these reactions can be carried out at a lower temperature. Typically for fully active Titania catalyst, we would recommend a first converter operating temperature between 575 degrees F and 600 degrees F. In terms of conventional alumina catalyst, all things being equal, to achieve the same level of hydrolysis, we would want an operating temperature of approximately 650 degrees F. Thus, the benefits of Titania, while ensuring high levels of hydrolysis of COS and CS2, we can also operate at a lower operating temperature. And this is not the only set of reactions that are taking place in our first reactor. We also have the Claus reaction taking place, which we know is promoted more so when we are able to reduce our operating temperature. Thus, most facilities employ Titania catalyst in their first reactor. Titania catalyst is more expensive than alumina catalyst, but we are able to protect our investment by ensuring that we do not have any unnecessary sulfur losses due to COS and CS2 that's not reconverted back to H2S across our first converter. How do we best protect our Claus catalyst? There are several ways or mechanisms that can deactivate our catalyst, including BTEX poisoning. BTEX commonly includes components including benzene, toluene, ethylbenzene, and xylenes. These compounds or components are contained in our SRU feed streams. If the BTEX components are not completely destroyed or combusted in the reaction furnace, they could impact our catalyst by cracking or polymerizing inside of the Claus catalyst. And on the next screen, we'll show a picture that will depict this. Furthermore, methanol poisoning is another issue that could take place in the SRU. However, methanol is typically readily combusted across the reaction furnace. However, there are some plants that do not process all of their acid gas in the reaction furnace. There is a bypass or a slipstream around the reaction furnace, and here we would essentially be adding raw acid gas containing methanol potentially and some of the BTEX components directly onto our first converter, which can directly poison our Claus catalyst. Both the BTEX poisoning and methanol poisoning is a permanent form of catalyst deactivation. Again, Titania catalyst does cost more than alumina catalyst, but it has significant benefits. One drawback is that in general, Titania catalyst is much more sensitive to BTEX poisoning compared to alumina catalyst. Another form of deactivation that could happen within our catalyst beds is what's called sulfation. Sulfation forms, and the mechanism is not that well known, but if we are able to allow for excessive or essentially free oxygen into our converter bed, it can coat the catalyst and essentially impact the ability of H2S and SO2 to get inside into the catalyst pores where the Claus reaction takes place. Now, typically, the SRU is absent of oxygen. However, in the front end at the reaction furnace, we are adding essentially a deficient amount of air or oxygen to burn only a portion of the total H2S. The mixing characteristics of our main burner for the reaction furnace could result in trace amounts of excessive or free oxygen to be carried downstream in our process to our converters. Furthermore, in advance of each Claus converter, we reheat the process gas such that we are able to tune in or approach optimal inlet temperatures such that we achieve recommended operating temperatures within our Claus reaction. Again, the reaction itself is exothermic, so we would want to specify an appropriate inlet temperature such that when factoring in the exothermic reaction taking place, our maximum bed temperature is in line with the recommended converter bed operating temperature. Sometimes these reheaters, the preferred method of reheat is an indirect method. Sometimes the reheaters are direct fired. We burn a portion of acid gas and sometimes fuel gas and introduce that and its temperature right into our process stream. Now, again, depending on the burner characteristics, and another issue that takes place is accurate metering of both the fuel stream and the air stream. Typically accuracy within 10 to 20% is deemed acceptable at a facility. However, it's these issues that could allow free oxygen into our beds and the creation of a sulfation mechanism that could impact the activity of our Claus catalyst. Here's a picture of a catalyst bead. Zoomed in, we see a pore or internal area available for the reaction to take place. BTEX that's not destroyed in the reaction furnace could enter the pore and either crack or polymerize inside of the catalyst, which would impact the Claus reaction that could take place. We see also with free oxygen a sulfation layer around the catalyst bead that could impact the ability of our reactants to get inside to the internal surface area for the reaction to take place. BTEX and methanol poisoning are a form of permanent catalyst deactivation. Sulfation is reversible. Sulfation is generated by excess oxygen that is present in our converter beds. There is a rejuvenation procedure, and if anyone has any questions on this, we do have a paper. A rejuvenation procedure would, instead of running a 2-to-1 H2S to SO2 ratio in our SRU, we would increase that ratio to, say, maybe 8-to-1. So we would have much more H2S in our process gas streams compared to SO2. The purpose is that this enhanced level of H2S would react with this free oxygen that's present in our bed. When we react H2S and oxygen in small amounts, we have direct oxidation to sulfur vapor. The reaction itself is extremely exothermic. Thus, in order to have a full-scale process where we took all of our H2S and had a direct oxidation scheme with oxygen, it would be hard to generate a process where we could have good control. The original Claus process reacted H2S over a catalyst with oxygen and directly produced sulfur. Over time, this process was hard to control, which led to what we have now, the conventional way to recover sulfur at gas plants and oil refineries by way of the modified Claus process, where we have an intermediate step at the reaction furnace where we produce SO2, such that downstream we can react H2S and SO2 to produce sulfur vapor, which is a more moderately exothermic reaction. Different types of deactivation mechanisms. Hydrothermal aging results when the catalyst is exposed to excessive amounts of water vapor over a long period of time. Hydrothermal aging is inevitable. The Claus reaction not only generates sulfur vapor, but it also generates water vapor. In general, the tail gas stream leaving the sulfur recovery unit contains upwards of 30% water. Again, hydrothermal aging is inevitable. However, there are opportunities to further protect our catalyst from what I'll call is excessive hydrothermal aging. If we have a thermal excursion or a sulfur fire in a bed, there is typically a line at the inlet where we could introduce steam, or sometimes, and more desirable, is an inert like nitrogen to snuff out the fire. We've seen it way too many times where there's been an upset in the plant, a steam line has been opened to a converter, and it was probably left open too long, which allowed excessive steam and essentially excessive hydrothermal aging of our catalyst. Thermal aging is caused by, I previously mentioned, sulfur fires or thermal excursions. If we have a sulfur fire, essentially a sulfur fire is the rapid production of SO2, so sulfur plus oxygen. This is common on SRU startups and shutdowns where we switch over from acid gas and add fuel gas to ensure that upon shutting down the SRU, that we are able to flush the system of all sulfur that may have set up over time. Any solid sulfur in our system will begin to melt. If we don't have a good fuel gas burn or sweep, again, sulfur plus oxygen can lead to sulfur fires. If we have a sulfur fire, it is easily depicted on the DCS by a rapid increase in temperature in our beds. In the notes, it mentions that it's just way too easy to achieve temperatures north of 800 degrees Celsius. Temperature excursions will always occur. There is no way around it. But again, this ties into the fact that our Claus converters are lined with castable refractory or fire brick to protect the carbon steel vessel shell from extreme temperatures. Temperatures above 1,000 degrees centigrade can result, for an extended amount of time, can result of the fusing of catalyst into large solid pieces. If we have that occurring, essentially we have jeopardized our catalyst and we have reduced the overall area for the Claus reaction to take place inside of our converter. Finally, soot deposition and liquid sulfur deposition. We want to operate our Claus converters at a temperature above the bed-specific dew point, upon which below liquid sulfur would form. Liquid sulfur will plug our catalyst pores and impact the ability of H2S and SO2 to participate in the Claus reaction in the inner surface area of our catalyst. Soot deposition is extremely common during SRU shutdown or startup procedures. Again, a proper SRU shutdown is carried out by a fuel gas sweep where we will burn fuel gas to achieve high temperatures throughout our system to melt out any sulfur that has set up, and also high mass flow rates to help push out any sulfur that's set up in our system. It is so imperative that during a sulfur or fuel gas sweep that we monitor and understand the burn stoichiometry of our fuel gas. We don't want to burn fuel gas with excessive amounts of air or oxygen because we know that we do have sulfur present in the system and we don't want to add oxygen to form sulfur fires. We also don't want to add too deficient amount of air because too deficient suggests that what we will have is the cracking of hydrocarbons into soot. If we are too deficient on our fuel gas sweep or burn, we will generate soot that will form typically on the top of our first converter bed. Thus, a lot of our work is centered around general performance evaluations of SRUs. However, we do support many of our clients going into formal shutdowns or turnarounds by ensuring that we have a properly carried out SRU shutdown and or startup. We will monitor the burn stoichiometry of the fuel gas, and the goal is to achieve a burn that is just ever so slightly substoic, such that we are not going to be generating soot and such that we are not going to be introducing an excessive amount of oxygen into our process, such that we can minimize the risks associated with both sulfur fires with excessive oxygen and also soot formation if we are operating too deficient. Soot that forms and sets up on our first catalytic reactor bed, upon restart up of the plant, we will see a high pressure drop across the converter. As a result, we wouldn't be able to process as much process gas as we are supposed to. Thus, it's always highly recommended to conduct a proper SRU shutdown and or startup in order to ensure that we reduce the risks associated with additional downtime coming out of one of these events to clear the soot from the first catalytic bed. We do have papers. We do have papers available if interested, where there is an online procedure to either melt out any liquid sulfur that is formed in our beds if we're operating too cold, and also a sulfur wash procedure which will remove soot on an impacted converter bed online. I did mention earlier that in terms of optimizing the Claus reaction, converter operating temperature is extremely important, and understanding what the temperature profiles across an entire converter could tell us in terms of catalyst activity and potentially when we should replace our catalyst. On the x-axis of this plot, we have bed depth, starting from the top and working to the bottom. And on the y-axis, we show temperature rise. The Claus reaction itself is exothermic. So as we are performing the Claus reaction, the temperature in our bed will rise. For fully active catalyst, depicted in plot A, with fully active catalyst, the majority of the Claus reaction is going to occur in the top portion of our bed. With time, for example, hydrothermal aging, which is inevitable, the profile will change. We will not have as much of a temperature rise in the top portion of our bed, and we will pick it up as we move down the bed depth. Plot C is representative of formal deactivation in the top portion of our bed, and we see that we increase our temperature or reaction across the middle portion of our bed. By understanding and always assessing our temperature profiles from the DCS, our operating team can have a good idea in their mind in terms of, one, are we achieving the recommended converter operating temperatures? And also, where in the bed, at what depth are we achieving that maximum temperature or equilibrium temperature? These profiles will change with time, with natural aging. All that information together can paint a very clear picture in terms of overall catalyst quality, or when we should maybe consider replacing the catalyst in our beds. We mentioned how a proper SRU shutdown and or startup procedure is very important in terms of preventing the formation of soot, which could lead to additional downtime coming out of a turnaround, which is not at all ideal. When new catalyst is installed in our converters, it is absolutely important that we take the appropriate steps to ensure that upon startup, our process is ready to process our acid gas. We see new catalyst here arriving at site on a truck in bags. Catalyst changeout, we have a crane that puts the catalyst in place above a manway at the top of our reactors. We see catalyst being installed. And we also see thermal wells, the thermocouples for temperature indication. Inevitably, upon install and the catalyst that arrives on site, not all catalyst will be spherical or cylindrical. There will be catalyst that has been crushed, catalyst that has broken. There will be catalyst fines. The big takeaway here is that it is so very important that we follow a stepwise blowout procedure where we isolate different pieces of equipment downstream of our converter, and we turn on our combustion air blower and ensure that we blow out all catalyst fines, crushed catalyst, any type of debris or material that we can in advance of a startup. By way of the force of gravity, materials that can get out of the catalyst bed upon startup could assist, if you would, in a plugging situation. The seal legs are notoriously known for plugging. Claus catalyst fines, dust, debris, plus sulfur can lead to plugging situations and would lead to additional downtime. If you do have any questions with respect to the stepwise procedure in terms of blowing out our catalyst bed in advance of an SRU startup, please don't hesitate to ask us. In terms of Claus converter and catalyst reliability and performance, it's always highly recommended to conduct an annual SRU performance evaluation to assess the level of destruction of contaminants in our feed gas streams to the SRU. We want to ensure that we don't have any contaminants like the BTEX components, benzene, toluene, ethylbenzene, and the xylenes that are carrying past the RF to our Claus converters. Gas testing and analysis will allow us to determine and prescribe converter operating temperatures relative to bed-specific dew point temperatures. Again, the reaction is gas phase, and we want to make sure that we're not forming any liquid sulfur in our beds. But at the same time, we know that the Claus reaction is favored as we do reduce our operating temperature. Direct measurements and determinations of Claus catalyst activity level, and also full assessments of oxygen levels, both from the reaction furnace and also from direct fired reheaters, to ensure that we don't have any sulfation in our reaction beds. And again, we talked about the formation of soot that could occur during a fuel gas sweep procedure upon both shutting down and starting up an SRU. It is absolutely imperative that we ensure a slightly stub stoichiometric burn of our combustion gas at all times. We don't want excess oxygen through our process. It will react with sulfur that is inevitably in or set up in our process to form SO2, a very exothermic reaction, also known as a sulfur fire. We want to ensure maximum mass flow rates of the combusted gases to push out and prevent any channeling that may have occurred during our operating process. And also, we want to ensure that our burn is not too deficient in air or oxygen to ensure that we do not produce soot on top of our first reactor. In general, the SRU itself is not a direct moneymaker. However, proper operations of our SRU is critical in terms of ensuring that our sulfur recovery license and goals are met. With proper operation and an SRU that is online, we protect our upstream moneymakers at our facilities, gas plants and refineries. Because the SRU is not a direct moneymaker per se, the unit itself is often neglected. In general, with steady operations, the SRUs run quite nice, which leads to the fact that from an operating perspective, they're often neglected and not that well understood by our operations teams. There's a common belief or commentary that we hear while on site that in terms of the SRU, steady operations are more than fine. Steady operations are definitely one important aspect. However, steady and optimized operations are extremely important, ensuring that we achieve desired sulfur recovery levels, and in doing so, we work to minimize our impact on the environment in terms of SO2 emissions from our stack, and overall, the less sulfur load exiting the SRU and out our incinerator stack leads to less fuel requirements to burn and overall less greenhouse gas emissions in the form of CO2. Again, while not a direct moneymaker, optimized SRU operations ensure that the upstream moneymakers are online and that our bottom lines are protected. With that is the end of the formal presentation. I just wanted to thank you again for attending. For more information, please do visit our website, www.sulfurrecovery.com. On their website, you will see ads for any future webinars that may be taking place, and you can also be notified of anything that we do by way of registering for our free quarterly newsletter. There are a couple of questions that have been asked in the questions tab, and I will formally answer them now. And after that, I will unmute everyone and you can ask me any questions that you may have, or feel free to type a question into the questions box or the chat box. The first question is, what is happening beyond the maximum bed temperature for Titania Catalyst? Titania Catalyst, as we discussed, is more effective compared to Alumina Catalyst in terms of hydrolyzing COS and CS2 back to H2S. A typical recommended operating temperature based on fully active catalyst, is approximately 575 to 600 F. For Alumina Catalyst, that temperature would be 650 F. We need more energy or temperature to achieve essentially the same level of COS and CS2 hydrolysis. What is happening beyond the maximum or recommended bed temperature? Well, it's important to remember that it's not only the hydrolysis reactions that are occurring in our bed. we also have the Claus reaction taking place. 2 molecules of H2S plus SO2 yield sulfur in the vapor phase. That reaction itself is favored at lower operating temperatures. So while we do pay more for Titania Catalyst, it is more effective at COS and CS2 hydrolysis at lower operating temperatures compared to Alumina. And at a lower operating temperature, we are able to more favor the competing or also occurring Claus reaction in that bed. If we operate above recommended or maximum bed temperatures, what we're doing is we're shifting our reaction scheme around, and while our COS and CS2 hydrolysis will still be good at a higher temperature north of 600 F, we're also moving away in an opposite direction from the temperature upon which we know, or the direction upon which the Claus reaction is more favored. Could you use both Titania and Alumina catalyst in one Claus reactor, specifically with Alumina in the top layer? This is an excellent question, and as I realize now, one important aspect that was not covered in this presentation. I did mention that Titania catalyst compared to Alumina catalyst is much more sensitive to BTEX poisoning if the BTEX components are not completely destroyed or combusted across the reaction furnace. Because Titania catalyst is also more expensive than Alumina catalyst, always our bed depth of Titania catalyst would be covered or protected by a thin layer of Alumina catalyst. Essentially what we have is we'd have a thin layer of Alumina catalyst covering our primary depth of Titania catalyst, and the idea here is that it's the Alumina catalyst that would take the brunt of any plant upsets that may occur, soot, BTEX that's not destroyed across the reaction furnace. So absolutely, when we make the investment for Titania catalyst, we do work to protect that investment by having a layer of Alumina catalyst on top. Typically, for a 3 or 4 foot bed, we'd have approximately 1 foot layer of Alumina catalyst on top. As we work our way down to maybe a 5 foot bed depth, we'd have 1.5 foot of Alumina catalyst on top. The next question is, in the case of a fire in our catalyst bed, do you recommend using nitrogen or steam snuffing? We talked about hydrothermal aging of catalyst, which is inevitable because the Claus reaction generates water vapor. There's nothing that we can do about that. However, in the case of a sulfur fire that from time to time can occur in our process, we would recommend adding the inert nitrogen to our converter bed over steam snuffing. Too many times there's been issues at facilities where steam was opened or used to snuff out a sulfur fire, and it was left open for much, much longer than it needed to be. So again, we would rather use an inert nitrogen over steam in terms of snuffing out any sulfur fires in our process. Next question. Is it unusual to have Titania catalyst loaded below Alumina bed? I believe that is tied into a question that I previously discussed in terms of that we want to protect our Titania catalyst, which is more expensive and more susceptible to poisoning from things like BTEX, by always having a layer, a sacrificial layer, if you would, of alumina catalyst on top. And another question, do you recommend or not recommend using excess air during startup and shutdown? I'll first answer the idea of excess air on a shutdown. In advance of an SRU shutdown, typically we would reduce or shut off our acid gas flow and start up our fuel gas and have a fuel gas sweep. The objective of the fuel gas sweep is to have enough temperature in our system and flow such that we melt out and also push out any sulfur that has inevitably set up in our process, whether or not that be along our lines, inside of the catalyst pores, sulfur that's maybe set up in condensers. That sulfur, upon remelting and vaporization, if we run excess air, that plus O2 will yield sulfur fires or the production of SO2, and that reaction itself is extremely exothermic. So no, we do not want to run excess air on a SRU shutdown because we know that in our process we still have sulfur in it. We don't want to run too deficient on air because at that point we will start cracking our fuel gas or hydrocarbons within the fuel gas and start forming soot. Thus, we want to run just ever so slightly substoic upon an SRU shutdown to protect best against both the formation of sulfur fires and also at the very low end or deficient end of soot. During an SRU startup, while not exactly recommended, we would again want to have a fuel gas sweep or reheat of our process method running again slightly substoic. However, in general, an SRU startup is only as good as the quality of the shutdown that we previously executed. If I have flushed all of the sulfur from my system during the SRU shutdown and fuel gas sweep, then there really is no risk of running excess air. But we always want to be conservative and again would recommend a warming or reheating of our SRU process during a startup with a ever so slightly substoic burn of fuel gas. Do you expect presence of iron sulfides in SRU lines and catalyst beds? Iron sulfides are very interesting and inevitably present in the SRU process. In general, the reaction of iron in the form of our SRU piping and sulfur, H2S, we will form a layer of iron sulfides throughout our process. The initial layer, if you would, of iron sulfide that's formed is actually very passive and serves as a protective layer against corrosion. Corrosion in the SRU is extremely problematic because we have moisture, we have piping, and we have sulfur. The problem with iron sulfides that's set up is the fact that they will burn when in the presence of oxygen. Thus, we've been at several startups and shutdowns in the past where we see temperature excursions in areas outside of a Claus converter, for example. For example, in the line leading from the SRU towards our tail gas incinerator, because we do have iron sulfides that's formed along the piping, and once we believe that all of the sulfur has been flushed from the system, we test for that by increasing the amount of oxygen. So very, very slowly and very little, we increase the amount of excess oxygen from our fuel gas burner sweep, and then we see that reacting further downstream due to iron sulfides that have formed that layer along our piping. So yes, we do expect the presence of iron sulfides in the SRU, specifically the SRU lines, and most specifically from the line leading from our SRU to our thermal incinerator. That is all the questions we have written out right now. What I will do now is I will unmute everyone, and if you would formally like to ask me a question, please do so. If not, again, thank you for attending our webinar. We'd love to hear from you. Did you enjoy the webinar today? Are there things that you would like to learn about or hear about in future webinars? We want to provide the information that is important to you. So any ideas or recommendations are very strongly encouraged. With that, I will unmute everyone and we'll see if there's any formal questions. And with that, we will conclude. I believe that everyone has been unmuted. I do see one more question that has come in, and the question is the rejuvenation of catalyst the same as reversal of sulfation? Sometimes I get confused and I mix the terminology up. There's a sulfur, a bed rejuvenation, or a bed revitalization. But in order to reverse sulfation, and again, sulfation is formed when we have excess or free oxygen in our catalyst beds, we are able to remove that oxygen that's set up in our beds by changing the ratio of H2S to SO2 in our system. We run a much higher ratio, typically recommended 8 to 10 to 1 versus the optimal ratio of 2 to 1 for our Claus reaction. That high proportion of H2S relative to SO2 will react directly with the free oxygen present in the bed, and H2S and O2 in low concentrations will have a direct oxidation to form sulfur vapor. That reaction itself is extremely exothermic and would be accompanied by a temperature rise that is higher than what is normally seen in the bed when running at a 2 to 1 stoichiometric ratio of H2S to SO2. So care must be taken when a rejuvenation or revitalization procedure is in place to reverse the effects of sulfation. And then one more question that's come through is, do we raise the inlet temperature to the reactors during reversing sulfation or a bed rejuvenation or revitalization? The answer to that question is no. In order to reverse sulfation, we we increase the ratio of H2S to SO2 to approximately 8 to 10 to 1 to react H2S directly with oxygen. It is not correlated or a function of inlet temperature. If in a bed, for some reason, our bed temperatures drop out, there's some issues with control, and we actually operate below the bed-specific dew point temperature for an extended amount of time, that is where we would want to raise the inlet temperature of our reheaters before that bed approximately 50 degrees above normal operating temperature, such that we're running hot to melt out or re-vaporize any of that sulfur vapor that's formed liquid and also potentially solid sulfur in the bed. Now again, the Claus reaction is favored at lower operating temperatures, and this would essentially increase the converter operating temperature. As a result, our overall recovery level would decrease while we are having this sulfur melt. However, we are able to have a procedure, an online procedure, that could turn things around without having to actually formally shut down the unit. So that is the advantages of having reversible, if you would, catalyst deactivation methods in terms of sulfation and also the formation of liquid sulfur inside our catalyst bed and in the internal pores, is that we can combat those online. During that work to reverse the effects, there will be a negative impact on recovery, but we're able to still keep running and it won't require a formal shutdown. I hope that answers that question. Are there any other questions? It doesn't appear to be so. With that, I would like to again thank you for attending our webinar today. I believe that one day after the webinar, you will receive a recording of the webinar and also a survey. It would be greatly appreciative if you could fill out the survey. And again, we want to be able to provide insightful information that's valuable to you. If you have any ideas or recommendations in terms of material that you want to learn more about, please don't hesitate to let us know. Again, thank you. Have a great remainder of your day, and thanks for attending. Goodbye.